All right. So, guys, starting again. So, in lab today, we are going to go into lab and we are going to study the energies that are released during neutralization reactions, right? And you guys understand that we're going to be really careful with energy. We're going to watch the energy go into the calorimeter. We're even going to track the energy that is released to the room because we're going to draw those graphs, right? And so we're going to do a really careful job of this today in lab. But then coming to 56 sharp, guys, question number 56 is exactly what this is going to look like on the AP test. But it's also exactly what this is going to look like when we do our next calorimetry lab. Because guys, what we're going to do, and we'll talk more third period, we're going to get these neutralization things wrapped up super quick. And then guys, we are going to start into a 4-day process where we are going to use not neutralization reactions, but dissolving processes like number 56. And guys, we're going to break up into teams and we're going to go into lab and we're going to figure out the heat of solution for a bunch of different salts. And then we're going to use spreadsheets to analyze and aggregate our data. And then we're going to project all of our data up on the wall and you guys are going to rip each other's data apart. When this is all over, guys, we are actually, it's a competition. And we are going to empirically be able to answer the question, whose data and calculations are the best? This goes to the winner. Is that Oscar? That's not Oscar. So guys, that's what's at stake. But now take a look at number 56. So guys, if you ain't got your books, get your books. Open up 56. All right. So for 2 of the groups that are in this room, when we do this next week, this is gonna be your salt. Ammonium nitrate. Guys, ammonium nitrate with diesel fuel makes amazing bombs. Oh, it's easy. You just look it up. There are actually websites that are talking about we need to take down all of the dams on the Colorado River because of the damage they're doing to the underlying anyway, which the damage is done. If we blow up the dams, it's not going to help anything. But guys, you can actually find websites where they talk about how to take ammonium nitrate and diesel fuel and drain Lake Powell.
We should try it.
What do you guys do on the internet? Never mind. All right. Oh yeah, because guys, ammonium nitrate is just lawn fertilizer.
That's awesome.
Say that again. Well, it's a fertilizer. Now you're scaring me. You know about fertilizer bombs. That makes me happy. Yeah, yeah. There we get into trouble because that's what they did at Boston, right? Yeah, that's a little scarier. Okay, so guys, all of that to say number 56. This is what these will look like on the test. This is what these will look like on the AP test. And these are the calculations that you're going to be doing when you do the second run at this lab. Here's what it says. 6.5 gram sample of solid ammonium nitrate dissolves in 60 grams of water in a coffee cup calorimeter. The temperature goes from here to here. Guys, let's stop. The temperature goes down. And guys, this is one of the things that's going to make the fight that is going to happen on this board in about a week especially contentious. Because guys, when you put ammonium nitrate in water and it dissolves, guys, the temperature of the water goes down. So is the dissolving of ammonium nitrate in water endo or exothermic? It is endothermic. It takes in energy. Guys, this is going to be a critical issue for us even today as we move into chapter 19. So guys, we know, think about this. We know that this is endothermic because the temperature of the water went down. But guys, do you see how that could kind of be counterintuitive? Because if temperature goes down, doesn't that mean energy goes out? It does. If temperature goes down, energy goes out. That's exothermic. So why is this endothermic? Exactly. Boom, because the water is the surroundings. Our system is absorbing that energy. And guys, remember in chemistry, we're always in the system. And so energy is going into the system, the ammonium nitrate, and that would be endothermic because the temperature of the water is going down, heat's going into the system, okay? Okay, so now guys, what we got to do is we got to figure out how much heat. But guys, this is where, and again, this is the fight on the lab. You've got to be able to tell the difference between heat and enthalpy change. So guys, check this out. And let me try this, just looking at the answers. So what we're going to do is we are going to calculate the amount of heat that is exchanged. So that would be the mass of the water. That would be the specific heat of water. And by the way, guys, did you notice I've been using 4.184 in the answers? The reason is because that value used to be on the AP equation sheet and they gave it as 4.184. But understand it's not on there anymore, but the equation is. Didn't we decide that? The value for C is not there, right? For water. Is that true? Okay, so guys, they'll give you the value on the test. You don't have to memorize it. I know we said 4.18. 4.184 is actually exact. Anyway, and then guys, the temperature change for the water. And guys, I would just set up your temperature change as positive and then deal with the signs later. So when we do that math, we come up with the value. Oh, that should be only 3 significant digits. So it should be 1960, but we're good enough, right? Now let me ask you a question. Is that the amount of energy that is lost or gained? Yes. That's the point. Guys, the first law of thermo says that is the amount of energy lost and gained. Now guys, because the temperature is going down, it's the amount of energy lost by the surroundings and gained by the system. So guys, when we come up with these Q values, they don't need signs because the energy could be going in or they could be going out. But then when we come up with our enthalpy change, then guys, this amount of energy was released when 6.5 grams of ammonium nitrate dissolved. We need to know the enthalpy change though in kilojoules per mole. And so to do that, we convert to moles and we convert to kilojoules. And this satisfies the second part of the question. And guys, this is also what you'll be doing in in this lab and the next lab. But now guys, what about the signs? Is that sign correct on the second answer? Guys, talk about it. Is that sign correct? Yes or no? So guys, let's let Nora bring us back. Go ahead. Hey guys, join Nora. Go ahead. Yeah, but let me make sure I'm with you. But what I think you're talking about is this calculation, right? Okay, so in that calculation, we don't worry about signs. That is simply the amount of energy that's being exchanged. So we don't care about direction because technically it's both out and in. It's just how much energy is moving around. You were really close. Hold on. Go ahead and grab it if you want. So that first question is about how much energy is moving around, and it's moving out of something and into something. But then when we talk about enthalpy changes, now we care about direction, and we are in the system. So is the positive correct? It is, because energy is moving into the system. We know that because the temperature change of the water is going down, so the water is losing energy. That energy is going into the system and so it would be a positive change for the system, which is the ammonium nitrate, and those numbers are in kilojoules per mole. Yeah. No. So that's interesting. So here we could think of this as positive or negative, right? It's moving in both. But the minute we talk about an enthalpy change for a reaction, that has to have only one direction. Because now we're talking about the interaction between the system and the surroundings. And now because we're talking about the system, energy doesn't flow both directions. It's either out or in, so we have to have a sign. Is that okay? Go ahead, Dan.
What if our number were to be instead of 24.1? Like what?
Are we talking significant digits?
No, like just.
Say it again. What?
So, hypothetically.
Yeah.
Okay. If you were to get from that equation.
Yeah.
And all of that.
Yeah.
A result of 0.
So let's talk about it. Right. So what would that mean? You ready? So if this value were 0, the only way that this could be 0 is if this could be 0. And if this were 0, the thing that would cause it to be 0 is if our temperature change was 0. Yeah? So what if that happened? What could possibly be going on if there was no exchange of heat? We have a name for it. Equilibrium. Guess what we're about to do?
No.
Go ahead.
Just to clarify some different figures.
Yeah.
The third number there for 56, 1958, without that 58 joules.
Yeah.
Should that be rounded to 2?
I think it should, because in the subtraction you only get 1 decimal place, so 2 significant digits. As I said 1960, I was like, shoot, the subtraction gives you 2. You're right. Yep. You guys okay? All right, now let's do this. So guys, then we get into the Hess's law, first of all by manipulation. This was a ton of fun to type. But guys, what we ended up doing was, for example, we had to flip this reaction, so I rewrote it flipped. Then we had to bring everything down. This adds up to this, so these add up to that. Similarly down here, a little more complicated, but the groove works. Then guys, over here, we started doing this using... Oh, my board's turned off. Guys, we started doing this using heats of formation. And when we did this using heats of formation, there we go. Then what we have to do, and guys, this is what you have to do. You have to write down the equation, then set it up again using your particular things from the problem, multiplying by the coefficients, identifying what heats of formation you need. Then guys, we plug in our numbers and then we do the math. So this is what these need to look like. You've got to have the equation, the specific setup, the numbers plugged in, and the answer. Questions on any of that? Go ahead. Oh, hold on. Bump. Yeah. Uh-huh. Yeah. Yep.
And then also the almost 502.
Yep.
So that doesn't matter which one you use. I mean,
Yeah, good question. And yeah, so the answer is don't let the oxygens be the guide.
oh yeah, but I'm saying like at the end, so then at the end you just use whichever one was last night.
So this is what I did. I said, okay, the first thing that I run into is P4O6, but that's over here, which means I had to flip this and change the sign. Then I skipped the oxygen because oxygen's messy. And then I found the P4O10, and I was like, oh, that's exactly where it needs to be. So I left this alone, and then I added them up. Now what's your question? No, and that's the beauty of this, is that, and this isn't just them picking just the right equations. The oxygens tend to just sort themselves out. So don't mess with the oxygens. Let them sort themselves out. And when you bring this down, we've got a P4O6. P4's on both sides. We have 5 oxygens here and 3 there, so we're left with 2, and boom, it adds up. So let the oxygens deal with themselves, because they always will. Yeah. Are we good, y'all? All right, so guys, do this. I need to record your homework performances. While we do, turn to chapter 19 in your book. And guys, I know that we haven't summarized this yet, which is going to put us at a little bit of a disadvantage. So I'd like to give you a moment to just skim over chapter 19. Guys, please do this on your own. You don't need to be chatting about it. Just all right, guys, here we go. So today comes with a couple disclaimers. Disclaimer number 1 is this, and we've built a culture of trust, right? That's us. We trust each other, so we can be real with each other. So guys, a week ago when we talked about the first law of thermodynamics, I told you not to Google it, right? How many of you did? Yes. Now this. Guys, the second law of thermodynamics, seriously don't. And that leads us to the second disclaimer as we get started. Guys, the stuff that we are going to talk about today and next time is going to be some of the most confusing stuff you've ever encountered in your academic career. So guys, my unenviable task is to try to steer you through a swamp full of scary things. So guys, ask your questions. It's going to get weird. Weird is good. But guys, you're also going to have to allow me the freedom to say, time out. We need to back away from weird because this is getting a little too weird. Okay? So guys, with that said, turning back to chapter 19, you're already there. I need to catch up. But guys, going back to chapter 19, did any of you summarize the chapter yet? None of you? Okay. So we're all sort of starting with the same blank slate. So guys, what you're going to find as you get deeper into chapter 19 is, guys, that chapter 19 piggybacks with chapter 15. And we've already talked about this. But guys, let's just thumb through chapter 19 together and let's sort of put our eyes on the big nuggets. You ready? So as we get into chapter 19, guys, the first thing that we run into is spontaneous processes. Then, guys, as we get deeper into this, we talk about reversible and irreversible processes. Guys, this is what we're going to do today. And you're going to find out that these are very tightly related. Then, guys, at that point, we're ready on page 805 to start talking about entropy. And guys, as we dig into entropy in 807, we're going to get into the second law of thermodynamics. Then, guys, at that point, we start getting into some ideas about how we understand entropy. Guys, this is 808, 809. We're going to do a little bit of this. Pausing on 809, notice the only word in bold on that page. And guys, the term is microstates. We will talk about that a little bit only because it's interesting. Then, guys, moving along from there, we get into more about these ideas of what entropy really is, and we'll talk. But then, guys, following that, if we go back to page 814, guys, as we then start on 814 and 815, we are going to start to quantify entropy. And guys, as we turn the page then onto 816, looking at the top, oh my gosh, an equation. Equation 19.8. Kind of looks familiar, right? Yeah, it's Hess's, well, sort of. It's Hess's law, but it's not enthalpies, it's entropies. So guys, we're going to talk about entropies of products, entropies of reactants, and bringing them together. Then guys, 817. This is the big idea. So guys, you don't need to go back in the book. But guys, what? Not back in the chapter. You don't remember, but let me refresh your memory. What was the very first thing that we talked? What's the very first thing in chapter 19? Spontaneity. And guys, please hear this. Chapter 5 and all of chapter 19 leads us to one and only one important question. If somebody were to ask you, hey, you did AP chemistry and you did thermochem, what was the big idea in thermochem? And guys, the answer is this: spontaneity. We're going to define it today. Let me give you a little precursor. Guys, spontaneous means a reaction that happens with no outside intervention. It happens all on its own. So guys, that is going to be our goal for this entire unit, is to be able to answer, does a reaction happen spontaneously? Now guys, here's the deal. There's only one way to answer this question, and it's page 817. It's Gibbs free energy. So guys, Gibbs free energy is the pinnacle of this entire unit. And when you turn the page again, and when you turn the page again, and when you turn the page to 822, guys, see that little unassuming table at the bottom of page 822? That is the last thing that we are going to do in this unit. That is the most important thing that we will do in this unit. Guys, that little table at the bottom of 822 is the takeaway message for this entire unit. But guys, we have a lot of work to do before we get there. Okay, so guys, what is the purpose of this entire unit? Is a process spontaneous? Now guys, we've already done some of the legwork for this in chapter 5, and you didn't even know it. But guys, what we're going to do is we're going to start into this more deeply today. So guys, with that said, now would be a good time to do this before we really get started. Guys, let's calendar together really quick. Uh-oh. Guys, hold on. For some reason, this didn't fully update. So guys, here's what we're up to. Today what we're going to do is we're going to get started with entropy, but we are not going to get done. This is going to be another one of those days where we are going to take the units or the day's notes, split it in half. So you won't have homework tonight in this class. You know how we've done that, right? Where we don't get done, we're like, you can do that anyway. So guys, your homework tonight is going to be to analyze your lab data. We'll talk. Then guys, on Thursday, we are going to wrap up what we start today by talking about entropy. Then guys, October, you ready? Oh, and then it's October. Guys, on the 2nd, we are going to talk about Gibbs free energy. But guys, remember, Gibbs free energy is that tie-in to the page, the table at the bottom of 822. So guys, on Monday, we are going to wrap up this unit. Then guys, on Wednesday the 8th, we're going to spend the entire day, or I'm sorry, Wednesday the 4th. Guys, we're going to rewrite our first unit test. How long has it been?
I really want my score.
Have you forgotten all the material? A little? That was the goal. So guys, you are going to be getting your tests back on next Wednesday, and we're going to spend the entire class period rewriting those tests. Then guys, we don't have school on Friday, which means when we come back on Monday the 9th, guys, we are going to take the test over thermochem. But guys, here's the deal, and this happens every year. We are not going to be able to take that test and get it rewritten before the end of the quarter. And so we're only going to have one test on first quarter's grade. It works out fine. We'll be okay. But guys, this is the way we're going to wrap this up, and then we're going to start into the next unit, which is all about electrons, chapter 6, and we'll start that on the 11th. You guys okay? Calendar is good? All right. So guys, with that said, here we go. Today we're going to start this conversation about entropy. Let me get rid of this. Let me get rid of this. And guys, here we go. Fair amount of notes. I would encourage you to be judicious. But guys, there are some things that we need to get down. So guys, what is the big idea? What is the most important concept in chapter 19? Spontaneity. Is a process spontaneous? Guys, that is the answer to the question, is a process spontaneous? So now let's define it. Guys, what is a spontaneous process? And for us, it's reactions, but we can talk about it more generically as just any process. But for us in chemistry, it's reactions. Guys, what is a spontaneous process? And this is going to be our working definition. It is a reaction that happens without any outside intervention. All right. So guys, at this point, your brain needs to become really, really, really plastic. Are you familiar with flexible? So guys, your brain has got to become flexible, because we are going to start throwing some ideas and some words around that you're going to try to make connections, right? We talk about how we learn by making connections. Guys, allow these connections to develop naturally over time. Don't try to lock in hard into ideas until you know it's safe, because guys, this conversation is going to go in a lot of different directions. Okay, so guys, this is then the question I have for you. And to have this conversation, let's not just have it about reactions. Guys, processes in general. So guys, let's brainstorm this for a minute. Guys, what are processes, could be chemical reactions, that you are aware of that happen all on their own? Go ahead. Ice melting. Let's pick at that for a minute. So guys, ice melting. Does ice melt all on its own?
If it's in too high temperature.
Ah, sometimes. So if we had a block of ice right now, would it melt all on its own?
Yes. Yeah.
Uh-oh. Now what?
Well, that means we need this to define what outside intervention is.
See how, right, see how where we've got to get a little flexible. So guys, first of all, let's connect it to temperature. So if we have a block of ice and the room is warm, will the ice melt?
Yes.
Yeah, but what if the room is cold? Okay, what if it's colder than 0 Celsius?
No.
Then the ice will melt? No, it will stay frozen. What if we add water at below 0? Then it will freeze. But you're right, we need to define this idea of outside intervention. We're not there yet, But guys, let's keep playing with the idea. Other things that happen on their own. Go ahead. Say it again. That's going to be our generic answer, because the sun. But let's talk about it. Are there processes going on inside the sun that happen all on their own? Yeah, absolutely, right?
I think that should happen on Earth. Just random uranium chunks.
Oh, yeah, yeah.
It's not uranium exploding, it's hydrogen fusing.
Yeah, but like fusion efficiency. Not at all. We're kind of close. Okay.
So, but what about this? Guys, if we were to track down Luke's idea about the sun, let's make an interesting connection. And it's kind of obtuse, right? It's the sun. But does the sun do sun stuff all on its own? Yeah. But guys, you ready for an interesting connection? It also loses energy, right? Sunlight. Let's keep going. What else happens on its own?
We looked at the diagram of dropping an egg.
Ah, all right. All right. And that's where we're going to start talking about reversible and irreversible. But guys, for right now, this is an egg. And if I hold this egg like this and I let go, what does it do? Falls. Do I have to do anything to that egg to make it fall? Yeah, so you have to let go. And this is the, where'd my egg? Oh, there's my egg. But guys, this is where we get into the subtleties of intervention. So guys, when we talk about this idea of intervention, we talk about the event and intervention. So guys, right now, is the event happening? It's not falling. So when we talk about intervention, it's from the moment that the event that we're studying starts. So this is not the event. The event is a free-floating egg in space. And guys, when we let go of that thing, it falls without outside intervention. But now you're going, wait a minute, what about gravity, right? And so guys, the idea here is that we could then say that eggs fall spontaneously in a gravitational field. But guys, the idea is that when we release that egg, it falls all on its own. Other examples of spontaneous processes, yeah? Yes. Guys, do elements radioactively decay without any interference from the surroundings? Absolutely. Check this out. Do they lose energy? They do. Yeah. Guys, other examples of spontaneous processes. Go ahead, Nora, just a second. Ooh, now we got to be careful. So, can photosynthesis happen all on its own?
Well, I mean, if you put sunlight and then like carbon dioxide.
Okay.
Oxygen.
Yeah, right. But in the absence of sunlight, does it happen? That's actually not photosynthesis, it's heat vents and sulfur. But, so guys, this is an important point. Does photosynthesis happen without sunlight? No. So does there have to be an outside intervention? The sunlight. But now guys, track this to energy. What direction is energy flowing during photosynthesis? In. Are we starting to make this interesting connection that guys, when balls fall, they give off energy all on their own. When things decay, they give off energy all on their own. But when photosynthesis happens, now it's energy in rather than energy out. Beckham, say it again. Tell me more about that.
Like how heat automatically goes from a colder.
Oh, brilliant. Thank you. Yeah, so when the word equilibrium freaked me out. So could we use the word heat transfer? And so the idea is that heat always flows from hot to cold, and we don't have to do anything to make that happen. That's brilliant. Keep going. Darn you. That's really good. Guys, diatomic bonding. If we have two oxygen atoms, Adam's going to hate this. So guys, if we have two oxygen atoms, do we have to do anything to get them to bond together?
No.
No, they just do it.
But they also don't
which is where we get into state functions and whether energy is in fact released. But for your example, Liam, we know that oxygen and oxygen bond together spontaneously. We don't have to do anything to make it happen. Guys, other spontaneous processes. Go ahead.
Spontaneous combustion.
Actually, kind of no, because it's really not Do you guys know about this?
We need to be absolutely flooded with alcohol in the air in open flame or something.
Well, no, actually, do you guys, so you know about spontaneous combustion, right? Somebody's walking down the street and all of a sudden they burst into flames. It's actually caused by alien death rays. It's really true. So guys, you've seen the videos, right? Slowly our government is starting to release all this information that we actually have aliens in meat locker and they have death. Okay, I'm kidding. But no, seriously, do you know that spontaneous combustion is a thing? And it's a very real thing in my world because I'm a woodworker. And guys, this burns down wood shops all the time because what happens is if you're finishing a piece of furniture, there's two types of finishes. This has nothing to do with what we're talking about, but we'll talk about it. So guys, there's two kinds of finishes. There are penetrating finishes and there are film forming finishes. So penetrating finishes get down inside the wood and they lock to the wood fibers. Film forming finishes, actually it's like coating a piece of wood in plastic. And it's a chemical reaction. Lacquer and things like that film basically a polyurethane. It forms a plastic shield over. So if you're doing this and if you're cleaning this stuff up with rags and then you throw the rags in a trash can, you can't throw it in the same trash can as anything because when you ball these things up, that finish continues to bond together and form the film, and that's exothermic. And if you ball them up, it creates so much heat that the rags will burst into flames. Spontaneous combustion. So how do you avoid it? You spread the rags out on the floor and let them dry, and then you throw them out. Go ahead. Are you sure? So guys, let me give you another stretch in terms of spontaneity. And so, Nathaniel, this is going to get even closer to your thought about we've got to define outside intervention. So, and I'm not going to light it, but you get the idea. So, guys, let's talk about where we are. What are things that we know to be spontaneous? Well, guys, we know that spontaneous things are like radioactive decay, like as Beckham said very insightfully, the flow of energy from hot to cold. We know that things like eggs falling, balls rolling downhill. Guys, all of these things are spontaneous, but what do they all have in common? They all exothermic. They all release energy. And then Nora threw us a curveball about the idea of photosynthesis. And we determined that that is not spontaneous because it is driven by the energy of the sun. Go ahead.
Would metabolism be considered spontaneous?
Here's where we've got to be careful, Dallin, because when we talk about metabolism, we're talking about biology. And biology, it is. It's so when you say metabolism, what's your system? Is it your body? Is it just that particular reaction? And it gets even worse. And guys, we're not going to talk about this a lot. I can't even use the word. What you're going to find out is that life has really interesting ways of getting around the second law of thermodynamics. It's fascinating, guys. I'll throw some videos at you on our GroupMe. Guys, life has amazing ways of fudging the books when it comes to the second law of thermo. Yeah. Yeah, which is far enough distant from this that it doesn't actually apply. Liam, just a second. Well, go ahead.
Would like the defining like forces of the universe be considered spontaneous processes, like gravity and like
Yeah, it's an interesting question, and the answer is they're completely separate. So forces are forces, and events are events. And forces can cause events like gravity, but we are talking about processes and events and reactions. The forces can cause those to happen, but it's not the event itself. Go ahead.
On that note, though, if you put two magnets coming together,
Yeah. Yes, absolutely. Because I have two kinds of magnets, ones that are really weak and ones that scare the crap out of me. We'll go scare the crap out of me. So these actually hurt. But the idea is, I wonder what they're round. I don't know what they're going to do, so let's find out. I got my fingers trapped between these ones. I cried like a child. That was cool. Okay, yeah. So Liam, this is kind of your idea. So guys, I know you can't see this, but do you know that it is actually physically impossible? It's physically impossible to get two magnets to hover in relationship to each other. Did you guys know that? It can't be done. You can't get two magnets to hover next to each other. Let me show you a better example. We'll play with these in a minute. But guys, the best example of this is bar magnets. We're going to talk because those aren't magnets. Those aren't magnets. So guys, this is the idea. If we put a magnet together north to south, they stick, right? But if you put them together north to north, they repel. But guys, what happens if I let go? They will not fly apart. What they'll actually do, and I can't really show this to you because they'll fall in gravity. But guys, what they'll do is one of them, oh, it did it. One of them will flip over and then they'll stick. You actually can't get two magnets to hover relative to each other. It's a fundamental rule in physics. Magnets don't hover. So you're thinking, what about this idea where you see these things and there's like smoke going off? Those aren't magnets. That's a magnet and a superconductor. And a superconductor is actually a really, really interesting ceramic that isn't magnetic, but it reflects magnetism. And so what a superconductor does is it sees the magnetic field and it creates a mirror image of it, and then they can float. But here's the question. Do we need to do anything to get these things to stick together? We don't. It happens spontaneously. We're going to keep going. So guys, now this. So what we understand is we have all of these ideas about these things that are spontaneous. They happen all on their own. So guys, what about this? What if I were to light the Bunsen burner? Is the burning of methane in oxygen spontaneous?
Once it's started, and if it's like it keeps being fed methane, yes.
Yes.
But it won't just start on it.
Correct. And now, and Nathaniel, you asked the question earlier, now we need to start talking about what it means for there to be outside intervention. Just a second. And so guys, this is spontaneous. The burning of methane in oxygen is spontaneous. Now you understand that if I open this up, this isn't going to burst into flames. We need to light it. But once this has been lit, guys, it will be spontaneous. So it's important that we understand we're talking about the process. And the process is the burning of methane. So guys, once we light this, and it's all about activation energy, but we can talk about that later. Guys, once we light this, do we have to keep going with the striker to continue to get it to burn? Once it's started, it goes on its own, and consequently, combustion is a spontaneous process. Does that make sense? Okay, so guys, let's then draw some lines in the sand, and let's talk about what we now understand. So guys, here's what we know about spontaneous processes. Thing number one is this: they lose energy to their surroundings. And guys, we talked about examples like balls or eggs falling downhill, hydrocarbons burning in oxygen, radioactive substances decaying, eggs falling to the ground. Guys, one that I came up with that we didn't talk about, nails rusting. Do we have to do anything to a nail to coax it into rusting? No, we just got to set it out in the backyard and let nature do its thing. What?
Isn't that what hand warmers do? Oh, isn't that what it heats up?
That's exothermic, yeah.
Thinking about cold weather.
Funny you should bring up hand warmers. We'll talk. So just a second, Nathaniel. But guys, this is an important point for us to tease apart some ideas. Guys, remember when I said that you shouldn't be latching a hold of things until you know it's okay? Guys, a common misconception that people have about spontaneous is they think it means fast. Guys, if this doesn't jive with your thinking, it's not in my notes, but you may want to make note to yourself. Guys, spontaneous does not mean fast. And you've also got to understand this idea. A process cannot become more spontaneous. It is binary. Either it is spontaneous or it is not spontaneous. You can't become more spontaneous. You can release more energy, but that doesn't make something more spontaneous. Just a second. Nathaniel beat you guys. Go ahead.
So on the ice melting or freezing thing,
Yes.
if we say that's still spontaneous, because it's not transferring cold.
Mhm.
That's
Right.
heat.
Yeah.
So that would be spontaneous because it's the air is moving.
That's, yeah, Nathaniel, that's brilliant. Would you allow me to couch that thought for 10 minutes? Because we are going to come back to that idea because it's a wonderful way to think about reversible and irreversible. So that's the other big idea that we're going to tackle today. And when we talk about reversible and irreversible, then we can do a much more intelligent dive into ice and water, and that's the time to talk about it. So let's couch that for a minute. Go ahead, Liam. Maybe. Maybe not. So let's talk about it. So if dissolving were spontaneous, what would have to be true? It just has to happen on its own, right? But guys, we now understand that the things that tend to be spontaneous, Dallin, I'm going to roll with this. This is too good to miss. So guys, here's what we've said. That things that are spontaneous, not about speed, about happens on their own, they release energy. And guys, Liam just threw us an amazing segue because he asked the question, what about when things dissolve? Is that spontaneous? And so guys, the answer is this. If we put something that is soluble, right? So not silver chloride, doesn't dissolve. If we put something that is soluble into water, do we have to do anything else to get it to dissolve? Dump table salt in water. Do we have to do anything to get it to dissolve? No, it happens spontaneously. Guys, what if we put alcohol in water? Do we have to do anything to get it to dissolve? No. I mean, we stir it sometimes to make it happen quicker. But guys, it's spontaneous, right? If it dissolves, it's going to dissolve. And we really don't have to stir it. It would dissolve on its own. We just stir it to make it happen faster, right? Does that make sense? So then, guys, if that makes sense, Guys, if that makes sense, explain this. Hold on. So guys, you shake it, and we're gonna have to share around a little bit. But guys, if you shake it, there are pellets in here, right? But if you squoze it, that is a word, squoze it, squeeze it. It's not a word, squeeze it. Do you feel that there's a bladder inside of here? And guys, that bladder is full of water. Now guys, around that bladder are pellets. Sharp, guess what they're made of? Ammonium nitrate. Now guys, squeeze this until the inner bladder pops. And guys, when the inner bladder pops, shake it.
I'm terrified it's gonna explode.
Did you get it to go?
We can pop it?
Yeah. Yeah. Did you get it? Yeah. Did everybody get it to go?
I think I lost the
Is it going though?
what?
Did you get it to go?
I'm just saying it really is.
Oh yeah.
There we go.
So guys, you got another 30 seconds to be fascinated by what's going on, but then we need to talk about it.
Wait, can we blow this up and do something?
Like spontaneous reaction. Spontaneous.
Yeah.
Are you saying that like as compared to other reactions?
We're going to do that in a minute. We're going to start comparing. All right, guys, join me. Yes, it got cold. But guys, this should cause you a little mental catastrophe. John, turn back this way. Guys, this is trouble. Because up until now, look at what we've established. In order for a process to be spontaneous, energy has got to be released. Guys, don't blink or look away for the next couple seconds. In order, you can blink. Guys, in order for a process to be spontaneous, energy has to be released. Now let's talk. Guys, when you broke the bladder, and you actually drew our attention to this, do you have one? Okay, say it quick. Guys, you'll notice that at the top it says instant. Why does it happen in an instant? Because it's spontaneous. Guys, you didn't have to keep shaking this. You didn't have to talk to it. You didn't have to coax it. The minute you got the ammonium nitrate together with the water, it started to dissolve. And it is spontaneous. You didn't have to do anything other than introduce them to each other, and it went. Just a second. So guys, is this process spontaneous? Is this process inside the quick cold pack spontaneous? Yes. Are you guys all okay with that? Now this, is it releasing energy? How do you know? Because it's cold. No, it's not about work. But guys, pause. This is the crazy new idea. And guys, you have never encountered something like this before in your academic career. But I love where your thinking went. Some of you are like, wait a minute, this thing is cold, therefore energy is going in. So how on earth could this thing be releasing? And the answer is not work. Guys, the answer is not work. Here's the problem. This reaction is releasing energy. But guys, it is releasing energy in a way that you've never thought of before. So guys, in order for us to understand this, we need to understand that energy is being lost to the surroundings, but guys, in a way that we have never thought about before. Guys, the problem is that our definition of energy is too narrow. So this feels cold. In whatever that problem was in homework, we calculated the cold. It was like positive 24 kilojoules per mole or something like that. Guys, that's a lot of energy going in. But now we have a problem, because we established before that in order for a process to be spontaneous, energy has to go out. But energy is going in. So how can this be spontaneous? And guys, the answer is energy is actually going out. It's just in a form that you have never considered before. So guys, don't hate me. We're not going to talk about how that's happening until Thursday. But I will give you a little bit of a teaser. So guys, up until now, as we talked about these ideas, we said that energy is being lost to the surroundings, right? And you were super comfortable with that because in your mind, the energy that you were thinking about was enthalpy. It's being released as heat. But now, guys, you're going to find out there's another way to release energy. It's not enthalpy, it's entropy. And guys, we're going to give you a little taste of it right now. Entropy is disorder. And we're going to dig into that more deeply on Thursday. But guys, what I want to do right now is I want to put you in this moment of crisis where you realize that yes, in order for a reaction to happen spontaneously, guys, hear this. In order for a reaction to happen spontaneously, it has to release energy. We're going to solve this with Gibbs energy at the end of the unit. But guys, it has to release energy. But that energy is not always in the form of heat. It can also be in the form of entropy, which is disorder. And we're going to talk more about that in the coming days. But guys, for right now, what we have to do is we have to tie this to another important idea. And guys, this is reversible and irreversible processes. So guys, don't let these quick cold packs be a distraction. But guys, we have two more terms to define, and then we're going to call it a day today. So guys, when we think about a process that is reversible, what does that mean if you just had to read the words and guess? Goes both directions. Sound familiar? Equilibrium. So guys, a reversible process is a process in which it is possible for the system to go back to its original state with no net change in the system or the surroundings. So now, Nathaniel, we're ready to talk about your idea. So guys, I know at this point in the year this is going to be confusing to you. What is this? It is not a beaker. It's a water glass. So guys, put some water in your glass.
It's a non-scientific beaker.
That's right.
A kitchen beaker.
Although, truth be told, I may or may not steal beakers and take them home to use as water glasses. Now guys, do this. No, they're new. Then guys, do this. Put an ice cube in the middle of your water glass. Just one is fine. Now guys, peg the temperature of this system at 0 Celsius. Is this melting or is it freezing?
Yes.
Yes. But guys, it's important for you to understand what that actually looks like. So guys, it looks like this. This is ice. This is liquid water. Now guys, these are at 0 degrees Celsius. And at 0 degrees Celsius, this is what's happening. Guys, which one has more energy? Even at 0 degrees Celsius. Which one has more energy, liquid water or ice? The liquid water does. Why? Because it has more freedom. Now guys, we're going to talk about that more in the coming days when we talk about entropy and microstates. But guys, even though these are moving the same speed, how do we know they're moving the same speed? They're at the same temperature. But guys, this one technically has more energy because it has more freedom. And so this ice molecule, this ice crystal is hanging out over here doing its thing. And this is hard. And this water molecule is over here doing its thing. And then guys, the water molecule crashes into the ice crystal. What happens to the amount of energy in the water molecule? It goes down. Where does the energy go? Into the ice crystal. What does that do to one of the molecules in the ice crystal? It melts it. And then this molecule goes off into the liquid state, and this molecule locks into the ice crystal, and what's the net change? 0. Guys, that is a reversible system. That is a system that is at equilibrium. So guys, if a system is reversible, is something happening? Yes. But guys, these things are happening in such a way that they undo each other and there is no net change. Like ice freezing and melting at 0. And guys, these systems are at equilibrium. Yeah.
So the reverse process is still.
And that's the way to think about it. Both the forward and reverse processes are spontaneous at the same time. Guys, let's pause. That is one that we should sit with because you're not going to like this. Ready? If you have a system that is reversible, is anything happening? Yes. Both of them are happening at the same time. So guys, in total, is anything really happening? No. So guys, when we, and this is where you got to be careful with your words. Guys, when we have a process that is reversible, it's at equilibrium, we do not consider that to be spontaneous. Because really, it's spontaneous in both directions, and as a result, there really is no event because they both cancel each other out perfectly. Is that okay? Now this. Guys, what about irreversible processes? So guys, an irreversible process is a process that cannot simply be undone by reversing the process. It still can be undone, but not by simply reversing the process.
Like an egg, where you could, all those molecules could be put back into an egg, but you can't operate it.
And we're going to talk about that in a minute. So guys, when we talk about reversible processes, these can go backwards. Guys, anything can be forced to go backwards. It's just that it doesn't go through the same pathway. It doesn't go through the same system of events. As a result, they have different values for work and heat. The forward and reverse processes have different values for work and heat. Now guys, when we talk about a reversible process like ice melting and freezing, the work and heat values are the same because they're simply just undoing each other. All right, so you ready for the deep thought? Let me go for a second. Spontaneous processes. So guys, spontaneous processes proceed all on their own without any outside intervention, right? We talked about that. But guess what? They are all irreversible processes. Guys, spontaneous processes, by definition, are irreversible. They always go in the spontaneous direction. They never go in the non-spontaneous direction. And as a result, anything that is spontaneous is irreversible. Guys, this is where the thoughts and the terminology get a little thick. So I'll give you a second to write it down, then we'll talk about it, then we'll talk about an analogy, and then we'll break. You ready? So guys, are you really okay? So guys, think about the things that we talked about that are reversible. Balls rolling downhill. Why do balls roll downhill? They release energy. Yeah, gravity helps. But guys, they release energy. But guys, if you were to sit a ball at the bottom of the hill, how long are you going to have to wait for that ball to spontaneously roll back up the hill? Never, right? And so guys, the idea is this. Can we take the ball and move it back to the top of the hill? Sure, but that is not the same process that it took to get to the bottom. Guys, it rolled to the bottom all on its own. We had to do work to get it to the top. Stop. Guys, this seems trivial, but think through that. So guys, here we have a ball, and the ball rolls downhill. Is that spontaneous? Yes, balls roll downhill all by themselves. So is it reversible? Is a ball rolling downhill reversible? No, because if it was, what you would see is balls rolling up and down the hill all on their own, all at the same time. So guys, that is not reversible, it is irreversible. But guys, be really careful with your definition here. Can something that is irreversible be forced to go the other direction? Yeah, but it doesn't happen on its own, and that's the difference. So guys, when we talk about spontaneous processes, they have a direction they always go, and they have a direction that they never go on their own. So guys, you ready for a really deep thought? All of the things that we talked about that were spontaneous, the decay of nuclei, the burning of hydrocarbons, the rusting of nails, guys, all of those things, they have a reverse process, but we never see them happen. Why? Because they're not spontaneous. So guys, we are surrounded by a world of processes that could go in both directions, but they don't. So the only thing that we see is the spontaneous process. We never see the non-spontaneous process. And guys, those are what we call irreversible processes. They can be undone, but they don't undo themselves on their own. Go ahead. Though by definition. So if we have something that is reversible, that means it is going in both directions at the same time, and that's equilibrium.
So, we still call, so if a system or like processes are reversible,
Yes.
we still call it spontaneous even though it's, like, that is spontaneous.
Yes.
The process
Yeah.
is,
Right. And so hold on, guys. Could we all take a big deep breath with Nora? Because guys, you are wrestling with exactly the thing that I was talking about. So many related terms and ideas. Take your time. Go ahead.
so pretty much the question is, are reversible processes and irreversible both are spontaneous, so they're like under or they're not?
We don't think of them that way. And here's why.
3 separate ideas.
So balls fall downhill, right?
Yeah.
And that is spontaneous because we can see it happen. When ice is melting and freezing at 0 degrees Celsius, do we see anything happening? No. So we say that nothing's happening. But what's really happening is both processes are happening at the same time. So it's spontaneous in both directions. We call that reversible. So if it's reversible, it's happening spontaneously in both directions. But we don't call that spontaneous. We call it equilibrium. So then when we talk about something that is spontaneous, it is irreversible. And that means it has a direction that it always goes, and it has a direction that it never goes. And that's spontaneous. Liam, is it on topic? Go ahead. Yeah, but the problem is that we can't do that vertically. We have to do it horizontally. So when you have a irreversible process, there's a net loss in energy. That's why it happens. When we have something that is at equilibrium, the transition has to happen this way. I love the way you're thinking about this visually, but when we have something that is reversible at equilibrium, it's a horizontal thing because the net energy change forward and backward cancels each other out. Is that okay? Go ahead, Nathaniel.
Right. So, if I'm somewhat comprehending this, reversible processes can't be spontaneous.
Hold on. Reversible processes, yes, but allow me to add a thought. So reversible processes are not spontaneous. In fact, they're spontaneous in both directions. But because we don't have a net change, we call them not spontaneous and therefore reversible. Equilibrium. Keep going.
Spontaneous processes are always irreversible.
You like the always. Hold on. Spontaneous processes are always irreversible. Yes, you can use the always there. Spontaneous are always irreversible.
There are irreversible processes that aren't necessarily spontaneous.
No. So anything that is irreversible is spontaneous in the spontaneous direction. So balls roll downhill, that's spontaneous. Can we get balls to go back? Sure, but that's not spontaneous. So those are interchangeable. Anything that is irreversible is spontaneous. Anything that is spontaneous is irreversible. Guys, chill for a minute. Go ahead, Liam. Yeah, the problem is that is so hypothetical because we're talking about elastic and inelastic collisions that to try to think through that would actually be a bit of a distraction. Guys, other thoughts? Okay, so this may be helpful, but guys, you saw the thing in the book maybe about the dropping egg, right? So guys, let's use this as a way to wrap this up. So imagine that we have an egg. And guys, if I'm holding the egg in free space and I let go, what's the egg going to do spontaneously? It's going to fall, right? And when it hits the table, it's going to shatter and break. Now, guys, is that process spontaneous? Yes, it happened all on its own. So is it reversible? No, it is not reversible. Guys, you can wait forever and this egg will never knit itself back together and magically leap up into your hand. But guys, does that mean that and listen to the words carefully, does that mean that we can't make that happen? In theory, could we knit that egg back together and lift it back up? Yeah, but you know what it's going to take? A lot of work. Huh? Right? It doesn't take any work at all to drop the egg. It does it all on its own. So guys, and this is interesting. You ready for this? Guys, check this out. When we drop the egg, that egg is not doing work. It is falling and it's doing its thing, if the egg's our system. But guys, could the egg go back up? Yeah, absolutely. But guys, the idea is we'd have to do a lot of work to make that happen that didn't happen when it fell. Now you ready for the weird thought? The amount of energy that is released when the egg falls and breaks is equal to the amount of energy that would need to go into the egg in the form of work to get it to go backwards. We just lost Sledge. So guys, this is the idea. Energy diagrams, right? Here we have our egg, and here we have mush. And the idea, guys, is when the egg falls down and goes mush, that releases energy. Kinetic is, potential is becoming kinetic. It goes in the, and guys, energy is released. But guys, if we want to knit the mush back into the egg, the energy change is exactly the same. The difference is the balance between heat and work. When that egg falls, most of the energy is released as heat. But in order to get it to go the other direction, we need more work and less heat to make that happen, and therefore the pathways are different. Mind thoroughly blown? Guys, we got to take a break. We're going to pause there, get out of here. We'll see you back in a few minutes.